Imagine you are in a ship, right? And you're zooming straight toward the center of a black hole.
Oh, wow. Okay, setting the scene.
Yeah, we're going right in. So from the outside, the physics of Albert Einstein work perfectly to describe what you're seeing. Space is physically curving. Gravity is just pulling with this immense force. Time itself is slowing down.
Right, the classic signs of relativity in action.
Exactly. But the second you cross the event horizon and you shrink down toward the singularity at the absolute center, the math just, well, it suddenly shatters.
It really does. It just falls apart.
Just starts spitting out literal impossibilities. The fundamental rule book of the universe just completely breaks down. And today, we're looking at exactly how to fix that broken rule book.
Which is, the ultimate puzzle. Because what you're describing at the center of a black hole, that is the exact crisis modern physics has been trapped in for decades.
Yeah.
We have the rules for the massive and we have the rules for the microscopic, and they absolutely hate each other.
They really do. And navigating that exact crisis is our mission for today's deep dive. We are unpacking an extensive review tailored specifically for you, our ThinkIQ viewers, of Brian Greene's landmark 1999 popular science audiobook, The Elegant Universe.
That's such a classic.
It is. Our goal is to give you a shortcut to being well-informed about the absolute bleeding edge of theoretical physics. We're talking relativity, quantum mechanics, string theory, and, the legendary hunt for a theory of everything without you needing a math degree.
Which I think most of us appreciate.
For sure. Okay, let's unpack this. Because to grasp the solution Greene is presenting, we first have to fully understand the disaster happening at the center of that black hole.
Right, because the source material, it isn't just handing you a textbook of answers. It's more of an invitation to experience the sheer wonder of how strained our reality actually is.
It really bends your brain.
It does. Greene takes these concepts that are honestly mathematically terrifying, and he translates them into this incredibly accessible, awe-inspiring narrative. But, to appreciate that awe, you first have to realize that the physics community is essentially standing on two spectacular pillars that refuse to support the same roof.
Yeah, let's lay out that battlefield for a second. On one side, we have general relativity.
Einstein's absolute masterpiece.
Right. This is our framework for the macro universe. It dictates the curvature of space-time, the orbits of galaxies, the mechanics of gravity. It operates on the idea that space and time are this smooth, continuous fabric.
And then on the other side, we have quantum mechanics, the framework for the microuniverse.
Of really, really small stuff.
Exactly. This governs atoms, subatomic particles, photons, and all the fundamental forces holding matter together. I mean, without it, the device you are using to listen to this deep dive right now wouldn't exist.
We'd have no modern electronics.
None. And both of these frameworks have been tested to astonishing, mind-bending degrees of precision.
But they operate on fundamentally incompatible logic. I've been kind of thinking about this like a board game.
Okay, a board game. I like that.
So imagine you're playing on a single continuous board. Half the board operates by the rules of chess.
Got it.
Your pieces glide smoothly across the squares. It's continuous, it's elegant, and highly deterministic, just like the smooth, curving space-time of relativity.
Right, that's a perfect representation of the classical macroscopic world. Smooth movements.
Right, but then the other half of the board operates by the rules of checkers. You can't glide. You are forced to jump from discrete square to discrete square.
It's quantized.
Yes, it's quantized. You have these sudden, jittery leaps, and you're no longer dealing with certainty, but with probabilities. That's the quantum realm.
Which is inherently unpredictable.
Exactly. You literally cannot slide a chess rook smoothly across a board where the underlying fabric of the game demands that you jump. The mechanisms just reject each other. But I guess my pushback here is, why can't we just accept that the universe has two rule books? Why do physicists insist they have to fit together?
Well, what's fascinating here is that for most of human history, and honestly most of the universe, this incompatibility hasn't really mattered.
Because they're usually kept apart.
Exactly. The universe usually keeps these realms totally separated. A star is massive enough that we can completely ignore its quantum jitters. And an electron is so small that its gravitational pull is, essentially zero.
So I imagine this only becomes a catastrophic problem at the absolute extremes. Like that black hole we just talked about.
Precisely. In a black hole, you have the mass of an entire star.
Which demands relativity to calculate that extreme gravity.
Right, but all that mass is crushed down into a subatomic speck, which demands quantum mechanics. You cannot use two conflicting rulebooks at the exact same time on the exact same object.
They just crash.
Or consider the Big Bang. where the entire mass of the observable universe was compressed into something smaller than a single proton.
Oh.
When you try to apply the smooth, continuous geometry of relativity to the violent, probability-driven jumps of quantum mechanics in that confined space, the equations literally self-destruct.
What do you mean by self-destruct? Like, what actually happens on the chalkboard?
You start getting probabilities greater than 100%, or infinite values for gravity. Basically, the math throws a fatal error code.
Which is impossible, right? The universe can't have infinite gravity. That makes no physical sense.
It doesn't. And the root of this mathematical disaster happens at a very specific scale. It's called the Planck length.
The Planck length.
Yeah. If you zoom in on space, past atoms, past quarks, down to a billionth of a billionth of a billionth of a centimeter.
That is unimaginably small.
It really is.
Yeah.
At this scale, you hit the Planck length, and the quantum jitters become so incredibly violent that the smooth fabric of space-time that Einstein envisioned is just totally shredded.
Shredded like paper.
Conceptually, yes. Up, down, left, right, before, after, the very concepts of space and time lose all meaning. Space just becomes this roiling, chaotic quantum foam.
Quantum foam. Okay, so if the core problem is that things get infinitely small, and at that infinitely small point, the quantum foam just destroys the smooth math of gravity, how do we fix it? We just can't have zero-dimensional points, right?
That is exactly the issue.
We have to stretch them out somehow to calm the math down. And I'm guessing that brings us directly to string theory.
That is the exact conceptual leap that theoretical physicists made, because standard quantum mechanics treats the fundamental building blocks of nature, like electrons or quarks, as zero-dimensional points.
So they have no physical size at all.
None. They're just infinitely tiny dots. But string theory says, well, what if they aren't dots? What if, when you zoom in on a quark, you find a one-dimensional, incredibly tiny, vibrating loop of energy, a string?
Oh, I see. By giving the particle a physical size, even a totally microscopic one, you somehow bypass that infinite crunch that destroys the math.
Precisely. You essentially smear the particle out over a tiny amount of space, and that slight stretching smooths out those violent quantum jitters just enough to prevent the equations from spiraling into infinities.
That makes sense.
Suddenly, the smooth geometry of relativity can finally coexist with the quantum world.
Okay, I see how getting rid of the dot fixes the error code. But how does replacing a dot with a vibrating rubber band explain the entire universe? Because the source material leans heavily on an analogy here, comparing the universe to a cosmic symphony.
Right, the guitar string analogy.
Yeah. If we look at a guitar string, it's just one physical object. But depending on the tension and how it's plucked, it vibrates differently to produce different notes. An A, a C sharp, and E. So are different particles just different notes played on these fundamental strings?
Yes, that is the core elegance of the theory. In this framework, there is only one fundamental ingredient in nature, and that's the string.
Just the string.
Right. An electron isn't a fundamentally different entity than a photon or a quark. An electron is just a string vibrating in one specific pattern. A photon is that exact same type of string, just vibrating in a different pattern.
Here's where it gets really interesting, though. I understand how a vibration makes a sound. But how does a vibration manifest as physical mass, or like a fundamental force? How does a vibrating string create gravity or electromagnetism?
Well, if we connect this to the bigger picture, we have to look back at Einstein's most famous equation, E equals mc squared.
Energy equals mass times the speed of light squared.
Exactly. Energy and mass are fundamentally interchangeable. They are two sides of the same coin. So when a string vibrates more vigorously, it possesses more energy. And because of E equals mc squared, that higher energy manifests in our physical world as a heavier particle.
Wait, really? So a heavy particle is literally just a string playing a really energetic, high-frequency note?
Exactly. And the pattern of the vibration also mathematically dictates the particle's quantum spin and its electrical charge. This elegance is exactly what gives the book its title, by the way.
The elegant universe.
Yes, because this is how string theory attempts its ultimate goal, unifying all four fundamental forces of nature.
Right. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force.
Yeah.
Four forces that operate on vastly different scales. I mean, gravity is exponentially weaker than the strong nuclear force that binds a nucleus together.
Which is why uniting them is the absolute holy grail of physics. In standard physics, gravity completely refuses to fit into quantum math. But in the mathematics of string theory, something miraculous happens.
What happens?
When you calculate the different possible vibrational patterns of these closed loops of energy, you inevitably find one specific pattern that has exactly zero mass and a quantum spin of 2.
Wait, isn't that the exact theoretical description of the graviton, the hypothetical particle that carries gravity?
It is. Physicists didn't have to awkwardly bolt gravity onto string theory. The math naturally generated it.
It's wild.
Right. The graviton is just one of the notes that the string can play. So string theory inherently includes gravity right alongside the quantum forces. It basically stitches your chessboard and your checkers board into a single unified playing surface.
Okay, the elegance of that is undeniable. I definitely see why it's captivating. But here is where the fine print kicks in.
Ah, yes, the fine print.
Because to make the mathematical music of this cosmic symphony actually work, the universe demands a stage far weirder than anything we see around us.
Much weirder, because we first have to accept how much Einstein already warped our understanding of reality. Space isn't just an empty box where things happen, and time isn't a ticking clock on the wall. They are a single, unified, physical fabric.
Space-time.
Space-time, exactly.
Right, and gravity isn't some invisible magnetic tether pulling planets together. Gravity is the actual physical warping, the sagging of this space-time fabric caused by heavy objects.
Which is hard enough to picture.
And because space and time are fundamentally woven together, your experience of time is entirely relative. It literally passes at different rates depending on your speed and the gravitational field you're in.
Which is highly counterintuitive, but definitively proven. I mean, we have to adjust the atomic clocks on GPS satellites because time ticks slightly faster for them out in orbit than it does for us down here in Earth's gravity well.
So reality is already stranger than our 8 brains evolved to perceive.
For sure.
But string theory takes that weirdness and completely shatters the dial. Because from what the review says, the math of string theory breaks down if it only operates in our standard 3 dimensions of space and 1 dimension of time.
That's right.
It flat out demands extra hidden dimensions.
Specifically, the equations require the strings to vibrate in 10 or sometimes 11 dimensions. If you try to run the equations of string theory in just our normal 3-dimensional space, the math spits out negative probabilities.
But a negative probability is impossible. You can't have a minus 10% chance of an event happening.
Precisely. It's a mathematical anomaly showing the framework is incomplete. But physicists found that when you give these strings extra spatial dimensions to vibrate into, those impossible negative probabilities mathematically cancel each other out. The math perfectly balances.
Okay, wait. That feels like a massive cheat code.
A lot of people feel that way.
If the math doesn't work in our normal 3D reality, physicists are just inventing 6 invisible spatial dimensions to force the equations to balance. Like, how is that science and not just science fiction? We can only move up and down, left and right, forward and backward. Where are these extra dimensions hiding?
It's a completely fair critique, and it goes to the heart of why this topic is so difficult to grasp. The theory doesn't suggest these dimensions are hidden in some alternate universe. It proposes they exist right here, everywhere around us, but they are curled up or compactified at a scale so incredibly microscopic that we simply glide right over them.
Okay, I need an analogy for this because 10 dimensions is heavy. Let's imagine you are looking at a thick power line suspended high up between 2 telephone poles, right? And you're looking at it from a mile away.
Okay, keeping our distance.
Yeah. From that extreme distance, the cable just looks like a one-dimensional line. It only has length. You can only conceptualize moving left or right along it.
Right. The physical thickness is totally imperceptible from that distance.
But if you were a tiny ant crawling on that exact same cable, your perspective completely changes. You can move left and right along the length, but you can also crawl around the circular circumference of the cable.
I see where you're going.
So to the ant, the cable has an entirely different dimension. The dimension that wraps around was always there. It was just curled up tightly and too small to see from afar. Does that make sense?
That is a brilliant way to visualize it. String theory posits that if we could shrink ourselves down smaller than a proton down to the Planck length, we would see that every single point in our familiar 3D space actually contains 6 additional tightly curled up dimensions.
Just folded up in every single point in space.
Yes. They take the shape of incredibly complex, twisted geometric structures known as Calabi-Yau manifolds. And the strings vibrate inside these microscopic, multidimensional knots. And here's the kicker. The specific geometric shape of these hidden dimensions determines exactly how the strings can vibrate.
Wow.
which in turn determines the masses and charges of all the particles in our universe.
So the shape of the invisible world entirely dictates the physics of the visible world.
Exactly. And to your earlier pushback about this being a mathematical cheat code, Brian Greene addresses this extensively in the text. He spends a significant portion of the book deliberately walking readers through established quantum mysteries to explain why these ideas challenge our everyday intuition.
Like what kind of mysteries?
Things like wave-particle duality, where light behaves like a spreading wave until you measure it, and suddenly it collapses into a single particle. Or the uncertainty principle, which proves you literally cannot know a particle's exact speed and position simultaneously.
Basically establishing that the universe at its core is already blurry, weird, and deeply unintuitive.
Exactly. The history of theoretical physics is full of math pointing to things that seemed absurd at the time. Black holes, time dilation, antimatter.
And all of those were later physically discovered.
Right. The math of string theory geometrically demands extra dimensions. It isn't a random guess to fix a problem. It's a strict requirement for the mathematical architecture to remain consistent.
Which brings us to the reality check. Because as elegant and awe-inspiring as a 10-dimensional cosmic symphony is, we have to look at the consensus on the source material itself.
We do.
While reviewers universally praise Greene's storytelling, giving the audiobook a 5 out of 5 for accessibility and his ability to make these brain-breaking concepts clear, critics, and many physicists, honestly point out a massive, glaring vulnerability in the theory itself.
It is the elephant in the room. String theory has incredibly limited experimental confirmation.
Limited or none?
Practically none directly. It remains an active area of theoretical research. It is mathematically rich, it's immensely beautiful, but we do not have physical experiments that can definitively prove strings exist.
Why not? Just a technology limit.
Yeah. To build a particle accelerator powerful enough to probe the Planck length where strings and extra dimensions live, you would need an accelerator roughly the size of our entire galaxy.
Wow. Okay, so what does this all mean? If you're a listener right now and I'm asking this on your behalf, if this topic requires you to fundamentally alter your entire view of reality, bend your brain around curled up dimensions, and it's not even experimentally proven yet, why invest your time into understanding it?
That's the big question.
Right? Why dedicate hours to a 4.9 rated popular science audiobook about a theory that might just turn out to be a beautiful mathematical mirage?
Well, this raises an important question, perhaps the most important question, about what science actually is. The most powerful lesson from the source isn't the finality of string theory, it's a demonstration of how scientific theories evolve.
How curiosity drives discovery.
Yes, it shows how pure curiosity and mathematical consistency drive us to the edge of human knowledge. Science isn't just a dusty encyclopedia of settled facts. It is an active, ongoing journey into the unknown.
It's the process of exploration, not just the destination.
Precisely. The fact that string theory forces us to ask profoundly new questions, to completely rethink the fabric of space, the arrow of time, and the underlying geometry of reality is exactly why it is immensely valuable. Unanswered questions are the engine of progress. I mean, without physicists willing to follow the math into deeply strange, unproven territories, we never would have discovered relativity or quantum mechanics in the first place.
That is so true. So for you, the ThinkIQ listener, looking for that shortcut to being well-informed, the verdict is clear. The Elegant Universe acts as an unparalleled introduction to modern physics because it weaves everything, cosmology, quantum mechanics, string theory, relativity, and human ingenuity, into one cohesive, captivating narrative.
It really does.
The ultimate takeaway isn't necessarily finding out if string theory is the undisputed truth. It's discovering that reality is vastly more intricate, strange, and beautiful than our daily macroscopic lives suggest.
And if we really sit with that, it leaves us with a rather profound, lingering thought that pushes a bit beyond the source. We've spent this time discussing how string theory requires extra dimensions, existing everywhere, all the time, curled so tightly that our human senses just glide right over them.
The invisible geometry of the universe.
Yes. If that framework holds true, and our 3D perception is completely blind to the higher dimensional architecture of the very space we occupy, it filters a larger question. What other fundamental massive truths about our daily existence are we entirely oblivious to, simply because our biology isn't equipped to perceive them?
Man.
We think we're observing the whole board, but we may only be seeing a fraction of the squares.
What an incredibly humbling thought. We could be completely blind to the symphony playing right in front of us. Keep questioning your reality, keep looking for the hidden rules of the board game, and keep exploring the elegance of the universe.